Hello everyone, welcome back to another episode of Leetcode in Swift. Today we'll be taking a look at Leetcode 78 subsets. So given an integer array nums of unique elements, return all possible subsets, which is basically the power set. The solution must not contain any duplicate subsets. Return the solution in any order. So it's quite similar to the previous problem that we looked at, combinations, and I can find quite a few number of similarities here. One being that it cannot contain duplicate subsets, which effectively means we want to find the combinations of all of these elements. It can be empty. It can have one element. It can have any number of elements, but it just should be a subset of this. So we have to find the power set. Right? So let's look at this. So when we have 1, 2, 3, we can have an empty one. We can have each of them singularly. We can have a combination of 1, 2, 1 and 3, 2 and 3, and then the whole thing 1, 2, 3. But can we have a combination of 2, 1? No, because we've already found it with 1. So it goes one way. So if you are thinking in terms of code right now, so your range will start, and if these are your elements, once you're at this position, you'll check only this part. Once you're at this position, so you'll only check this. Once you're at this position, you'll only check this. And once you're at this position, you won't have to check anything, hopefully. So that's kind of like the question. Let's look at the solution. So this definitely will need to be solved using a brute force method. I'm going to be using backtracking with this, with recursion in the code, but let's look at the conceptual overview. So given we have these three elements here, 1, 2, 3. So if we pick one, like at this point, we have two choices, right? Either we can pick this one or we can leave it out, right? And these choices not only exist for 1, but they also exist for 2 and 3. So here we have two choices, here we have two choices, and here we have two choices, which means we'll have effectively 2 to the power n number of combinations that we can find, right? Keep that in mind. So let me draw out the backtracking graph here. So let's start with the node up top. At this point, we have a choice to add 1, or we have a choice to keep it empty, right? At this point, we have not reached here, so we're dealing with only 1. So this is level 1. And let's continue. And after we have this point, and the next choice, we have either to add it to or nothing, right? So this part of the tree will become 1, 2. This part will become a single one. Similarly, on this side, we either have a choice to add 2 or nothing. We add 2 here, and this would just remain nothing, right? This is level 2. Notice that at every level, the number of elements are increasing with the power of 2 to the power n, right? So at this level, we have 2 elements, which is basically 2 to the power 1, because this is the first level. At this level, we have 4 elements, which is equal to the power 2, the second element. If you continue down, you will notice that it increases with this rate. So let's continue. So at this point, we have 2 choices again: keep it empty or add 3, because that's the next element. If we add 3, it's going to be 1, 2, and 3. And this would remain 1, 2. right? At this point, we have two choices again, keep it empty or add 3. Then if we add 3, it will become 1, 3, and this stays 1, right? Let's take a look at this. So we have a choice to add 3 or nothing. This would become 2, 3, and this would yield us only 2. And again, at this point, we have a choice of adding nothing or adding a 3 again. If we choose to add a 3, we would get a 3. If nothing, it just remains nothing. So if you notice at this level, we have 8 elements, 2, 3, 4, 5, 6, 7, 8. And that's equal to 2 to the power 3, right? So since it's 2 to the power 3, we can actually deduce the time complexity of it, right? It's gonna be, we're gonna make n operations on 2 to the power n elements. So it's the time complexity, the worst case scenario, it's gonna be 2n 2 to the power n. And as I told you, this is brute force. It's not really efficient. So we're gonna have something very weird like this over here. So this is actually the backtracking solution. If you want to see how to code it, let's jump into the code editor on Leetcode. Hey everyone, let's see how to code this up. So we'll need a result variable, which should be of the type this, nested int array. And we need a temporary variable which would carry the current path that we are following in the tree. So this would be an array of int. Okay, and we create a function called backtrack, just like how we did in the combinations solution. This is going to have the path that we're going to pass in with this temp variable. And this is going to be in-out method because we want to give it back to the function as a parameter. This would be of the type int. Then we would have a max value which would control the index of the nums inside the backtrack function. This would be of the type int, and then a target which should keep track of all of the levels, like the level we are at. So if you're at level 0 or level 1 or level 2, it would pass in this, and we'd only check for the elements that are more than that level, right, in the nums array. And we want to call this, we want to pass in that target, right? So we want all of the levels in 0 to the range nums.count. We want to take all of the levels from 0. So 0 is when there's no element, and then first level is when we add 1, second is when we add 2, 3 is when we add 3, and this is what the levels will give us. So we can call the backtrack function in here. This will be called 3 times in the case of this, no, 4 times in the case of this, since we're starting from 0. We will give the temp variable. Now this max value, initially we want it to be -1, because since we don't have any values in our path, we know that it can be, since we're starting with zeros, inside also we'll be starting with a 0, the index. Initially it can be -1, so that we can call that backtrack recursive function inside in here. So you'll see what I mean. And then for target we pass an I, and after all this our res value will be populated, and we will just return res. Let's take a look at inside the backtrack function. So this target gives us the level we're at, right? So from the level we can determine how many elements are there in this path, right? So if we reach that targeted number of elements in that level, we can append it to the resultant variable, right? All of the paths in here. So we do if path.count double equal to target result.append. Now in here, I want to map the variables, the elements inside path with nums, because if you notice, we're not really giving any and doing any calls to nums yet. So this nums is supposed to give us the current element we are looking at. And once we get that, it will append it to result. And then we can return it, because that means the backtrack function has succeeded and we have to go back to the next level. And this is the base case for this recursive function. Now for the actual work we want to put in, we want to check in index from max plus 1, since we gave -1 here first. We want to start with 0. So for index and consecutively every other calls, this would keep incrementing, right? So for index in max plus 1 ... less than nums of count, this would take us to nums.count -1. That would actually satisfy all of the elements inside nums. And now we want to add path.append. You want to append the index of that position, right? Because here we are getting the elements from that position. We want to index the path for that, and we want to append the index for that position. And then we'd call the backtrack function again, which would pass in the path variable and index, which would only taken from I minus 1 onwards, -1 plus 1 onwards, which is 0 in the first iteration. And then we would pass in the same target we were at, because we want to see the level and we want to explore the current level we are in, right? And then once we're done with that, we just want to simply pop last from the stack that we have in here. And that's it. That's the solution. Let me give it a run and see if it works. What's the error here? Oh, this should not exist. My error. Okay, that runs. Run all example test cases. Submit. Voila. Awesome. This was an easy solution. As you can see, like, there's a pattern to the backtracking solution. If you notice from the previous problems we solved. If you have any questions, let me know. If you like these kind of videos, give it a thumbs up, subscribe. I'll see you guys in the next video.